All right, and so let's now look at how we can handle the trig integrals in the family where it's a power of sine in product with another power of cosine. Okay, so a power of sine multiplied with a power of cosine. Okay, and that is one trig, big trig function. Okay, and let's look at a few examples in this family so that we can recognize some generalization right there. Okay, so this is the family that we are heading into. It's a product of a power of sine and a power of cosine. Okay, and so now to continue with that with the earlier earlier example, now allow me to introduce example 3 right here. And again, this is all about we want to evaluate with different integral problems given to us. So the one we're looking at here is, yes, it's an integral. I am expecting a power of the sine and a power of a cosine. So let's look at how about sine to the 6 of x, okay, power 6, and then cosine to the 7 of x. And that's what I meant by a power of the sine in product with a power of a cosine. Okay, so it could have also been, this is a different problem, but it's in the same family. For example, it could be a sine to the 7, okay, and cosine to the 4th. See, the sine gets a power, the cosine gets a power. These two stay in a product, and it could also be, sine to the 6 of x times a cosine to the 6 of x. The two powers can also equal, but that stays in the same family. But so now, what I'm looking at here in this specific example, in this specific problem, is that among the two powers here, among the two powers that appear in our problem, one of them is the power for sine, the other one is the power for cosine. Then here's a note that I want anyone viewing this video to realize right here. Here's a little note I would like to make. Okay, you see this power right here? Among the two powers available here, one power is odd. Okay, as long as one of the powers, okay, one of the powers is odd. That's what we notice. Okay, if both, that's even. We will have an example on that, but at least this is the case I purposely brought people in right there. So another situation could be an odd power on the sine right there, and even power on the cosine. That's another case like this. You see, one of the two powers is odd. This guy is odd. That guy is odd. Okay. So now, if that's the case happen to us, we have an integral. Again, it's a trig integral where it's a combination of a power of sine with a power of cosine, and one of the two powers is odd. And so here we recognize the odd one is the one on cosine. Okay. So the method I'm about to introduce here, we don't have the reduction formula for this, because the reduction formula only works, has a limitation. It only works on the single powers. Okay, so it's pretty flexible, but only on single powers. Now we got a mix of two different powers of two things here, sine and the cosine. Then we have to start being a little more creative. So I pointed out about there's one of the powers here is odd for a good reason. So now right on that odd one right there that we recognized, this is what I'm doing. The even ones, I'm leaving it the same. Okay, but the odd one, I'm going to purposely separate out one lone factor. It's similar to that technique I introduced in example 2. So I had to introduce that technique in the earlier example 2 so that people start having some experience with that. So this is now going to give me cosine to the 6, okay, of x times cosine of x. And that's what we purposely do, times cosine of x. So this lone factor is purposely separated out. Okay, and so now in that way, here's what I'm seeing. In my next step, I am still going to leave the sine to the 6 the same. Sine to the 6 of x, I'm leaving that the same. This cosine, but this now even power, this remaining power on the x after the separation of that single factor right here, then this cosine to the 6, I am going to write it as a cosine squared of x, but to the third power. And then all of the remaining stuff right here, there's a cosine of x dx. Okay, and so now we learn from that experience we've done in example 2, right, that specifically the later technique, aside from the reduction formula, then this is what I'm doing. The cosine square can again be expressed as 1 minus sine square. Ladies and gentlemen, the algebra is so important. Here specifically, I'm talking about the algebra on trig functions. Okay, that's why we call them the identity. They are permanently true so that you use them anywhere. So cosine square is permanently equal to 1 minus sine square. And that's what I'm about to do here. So now the first factor sine to the 6 of x stays the same. But now I have 1 minus sine square of x to the third power. Okay, and then multiply with the lone factor cosine of x dx. And so now alongside with that experience we have already learned from example 2, and this is what I'm doing. I am about to use a substitution method. Again, I am going to substitute u for sine of x. That's what I'm about to do. Okay, and so after viewing example 2, then anyone should have a clear picture in mind right here. All right, so if u equals sine of x, then consequently the derivative du dx has to equal cosine of x. And now realizing that this symbol here is not only a symbol, it also means it's a fraction, it's a ratio of two differentials, du over dx. Then we can rearrange this entire equation here as du over cosine of x to equal dx. Okay, and so now I'm ready for a final action right here. All right, and so this gives me, so in the next step, our current integral after the substitution becomes, so the sine to the 6 now becomes a u to the 6 because sine of x gets substituted away by u. Okay, so anywhere you see the sine right here, sine is substituted away by u. And so all of these signs right here get substituted away. And so just like alongside with how I've been explaining that in my video lecture about the substitution method, then anywhere you see the sign, you have your freedom to substitute away. And 1 minus sine squared, so now it's 1 minus u squared cube. Okay, but the cosine did not get a substitution. It's okay, we'll find out. And then the dx right here, we found a substitution that I pointed out earlier in the other board. So now it's a du over cosine of x. And so now this cosine of x left over that we didn't find a substitution for that. At first it became a little worry, but now we can cancel that away. So it's strictly substitution method that resurfaced here in our lecture, here in our lesson that we're learning. So at this point it is highly recommended that to go ahead and review your substitution method technique that you've learned right there. Okay, so the integral now becomes it's u to the 6 times 1 minus u squared cube du. It's a completely brand new integral, ladies and gentlemen. It's in terms of u, but this thing here is very manageable. Very manageable. But I'm not saying it's going to be a short one, but it's a very manageable. It has a clear way of handling it because all I see here is a polynomial. Yes, it has a power of 3 here, but we can always FOIL that out, okay, and distribute that power 6 of the u into each term. So let's complete that. So this 1 minus u squared, or how about anyone here viewing this video lesson should be fluent enough with the algebra, allow me to start picking up pace a little bit here. But so that all of that here is the same as, so I'm still leaving that u squared, but it's a 1 minus 3 Okay, minus 3u squared plus 3u to the 4th power and minus u to the 6th power. That's how we FOIL out all of this and quickly get into that. And then in the next step, we can distribute out the u into each term like that. Okay, and so to become, we're looking at an integral of u to the 6th minus 3u to the 8th plus 3 times u to the 10th minus u to the 12, all the crazy high powers. But in the end, like as I said earlier, this is a very manageable integral because they're all just power rules applied here. Okay, so our final integral in terms of u by far, the antiderivative here is going to be 1/7, okay, u to the 7 minus now 3/9 times u to the 9th power. And so notice later we can cancel that 3 into the 9 right there. Plus, now it's 3/11 times u to the 11th power. Okay, and then minus, now we're looking at 1/13 times u to the 13th power. And don't forget, plus c there. Okay, and so now the last step here is to bring back the original substitution where u was substituting for sine of x right here. Okay, and so I have left this here long enough. I need some space to write my steps. So allow me to erase this small part right here because I want to leave the other structure there the same so that people can have a sense about reminding yourself what happened in each of these steps. All right, and so now I'm looking at in the next step, first term is going to give me 1/7, okay, times sine to the 7 of x minus now 3/9 from the earlier board, from the other board. 3/9 here becomes 1/3. All right, so minus 1/3 sine to the 9th of x plus, now we're looking at 3/11, okay, sine to the 11 of x, and then minus 1/13, okay, times sine to the 13 of x, okay, plus c. All right, and so this is our final answer. All right, and so we've made a long way, and then let me remind it. So we made that substitution u equals sine of x here. Okay, and I didn't have to remind anyone else about all of that other fancy stuff after the substitution. But so the critical changing point here, I mean the point of recognition here that we recognize where to go is that one of the two powers. So yes, it's a combination of two powers of a power of sine over a power of cosine right here. But one of the two powers here is odd. Okay. That's what happens. And then so once we recognize an odd power among these two, we tackle down immediately on that odd one right here and separate it out, that one factor right there. That's the generalization of the work right here. And then so after we separate it out, and it gave me a remaining supposedly even. And then for the even one, we purposely wrote that as a base being a square right there, and then raised to a whatever power coming out as a product of these two. Okay, and then from there on, we use our trig identity to turn that into, you can see that they are the same expression now. Okay, all right, and then we substitute away, and then we let ourselves into a function, an integral completely in terms of the new variable u right there, and then we handle that quite easily. Okay. All right, so let's come up with a generalization right here. So again, the kind of problem that we're getting into is a power of the sine and a multiply in product with a power of the cosine. Okay, and so if one of the two powers, as long as one of the powers here is odd, So we can say that, hey, out of the two powers here, let's isolate out one case right here. If the n here is odd, and again, odd here means a 2k plus 1. If the n itself is odd, and disregarding whatever happened to the other one, as long as we recognize 1, then on this odd power right here, on this odd power, and of course disregarding the other one, if we recognize that one, then we can purposely isolate out our starting problem here. It's a sine of to the 2k plus 1x times a cosine to the m of x dx. Okay, and so that generalization we have seen earlier. So right from that recognized odd power, I am going to rewrite it as sine of the 2k, now even. Okay, sine to the 2k power of x to the even, and then multiply with cosine to the m, whatever that power m is, as long as we recognize one of them. So kind of like we chose one of the odds right there. Okay, and then times with the sine of x dx. We separate it out. So right from that, I am going to see sine of 2k. So it's the same as, I'm seeing that as sine squared of x to the k power, okay, and multiply with cosine to the m of x times sine of x dx. And so from this point, we are going to use that trig identity. Sine squared is to become 1 minus cosine square, okay, to the k power, and then multiply with an extra power m, and m could be odd as well, and I'll navigate into the other case as well. Okay, but right now specifically we're worrying about if n is odd. Okay, and then here it's a sine of x dx. And so now mostly these are all cosine. So there's, except for that lone power, except for that lone factor sine of x. So here we substitute all of the cosine expression by a u right there, and then the substitution method carry on from there. Okay, so on the other hand, in this generalization, if our power, if we recognize that the power m is odd, okay, if that power m is odd, and so like I said earlier, if one of the case, so here we have a power of sine coming together with a power of cosine. So if we recognize one of these two to handle one of these two as an odd one, and that's if we specifically focus on the sine as an odd one, then that's how we handle it, and disregarding the other power. But now in case where we recognize cosine is the power that's being odd right there, then of course our cosine is as following. Our integral is going to look as following. The integral at start, the power n on the sine remains the same. Okay, it could also be odd. Okay, but now we specifically focus on that cosine of, and that power of cosine being odd. And so here it's cosine of 2k plus 1 of x dx. Okay, and so now in this case right here, specifically like the case we did in example example 3 earlier, that I separated out that lone factor of cosine right here, because there's that plus 1 power in the power. So that means here in the next step, I am going to write this as sine to the n of x times cosine to the 2k of x times cosine of x times dx. Okay, and so in that way, this is going to be, all right, so sine to the n of x times, and that's cosine right there. I'm going to purposely rewrite it as cosine squared of x to the k power times cosine of x dx. All right, and so now that's, in the next step, it gives me sine to the n of x, okay, times, so now that trig identity can be used again for that squared of cosine right here. So here we're looking at 1 minus sine squared of x to the k power. Okay, and then with that lone factor, cosine x dx. And so at this point now it's clear, it's become so clear that we substitute sine of x to equal u right there. So we're going to let u to equal sine of x, and from there our substitution method will carry along. Okay, so this is the generalization of how we handle the kind of trig integral where it has one power, it comes from one power of the sine with one power of the cosine right there, and we specifically recognize that, hey, one of these two powers is an odd one right there. If one of those two powers is an odd one. Okay, and so now we are going to look into example 4 to apply what we have just learned earlier about some generalization that we have had on the board. I noted down earlier. So in this example 4, again we are evaluating. Okay, we want to evaluate the following trig integral. Let's say we have sine to the 7th of x, okay, times cosine to the 5th of x, okay, dx. All right. So this example is delivered after I made that generalization. So it's our trig integral is in that family where it comes from one power of sine and another power of the cosine. So one power of the cosine and one power of the sine. And so now on both of these powers, see, it's even better than what we've done earlier in the example I've done earlier in example 3, and in the generalization. As long as we recognize one odd powers, one of the powers here being odd, then we can tackle down right on the odd. But so now both of these are odd. The truth is, if both of these are odd, you can tackle down on any one of them. You can tackle down on any one of them. Okay, so let me deliver two solutions. So how is it possible that we can do two solutions? I mean, aren't these problems so challenging that why is the teacher up here giving two solutions? All that is made possible to do two solutions because we have two different options here. We have one option is to tackle down on that odd power of the sine, or we can tackle down on that odd power of the cosine here. That's why we can end up with two routes, two solutions. But they are completely similar, very similar. So something that you might want to watch out for in case you run into a problem like this. Okay, so and I will introduce more details as we go along. Okay, so here's what I see. How about right now I see the lower odd power here being the 5, being the 5th power. So I'm going to choose this 5th power and leave that one there the way it is. So now I'm going to, just like that generalization that we have picked. So now if I only focus to this odd power of the cosine right here, then I'm leaving the sine to the 7 the same. Okay, and I'm looking at this cosine to the 5th as a cosine to the 4th of x times cosine of x. So the permanent technique here is to isolate our one lone factor from your recognized odd power of either one of the two functions, of the two trig functions. Okay, and now once we have separated out that, then the remaining power here on the cosine has to, of course, be even. But see, right from there, that even power now becomes, well, first of all, the sine to the 7 remains the same. But that cosine right here is indeed, we thought of that as, we're going to think of that as a cosine square of x, and squared again, and then multiply with that lone factor cosine of x. And that's why, so now just following directly with that guideline that we have seen earlier, then this is going to be sine to the 7 of x times all of that cosine square here. We can rewrite it as 1 minus sine square. 1 minus sine squared of x, okay, square, and then multiply with cosine of x dx. Allowed me to kind of cut that dx down into the next line because I ran a little short of space right here. Okay, so now that means here anyone viewing the video can start seeing things ahead already. I am now going to use a substitution for u equal sine of x. And so in that way, du dx is going to be cosine of x. And that means in the next step I can rearrange this and make that into du over cosine of x to equal dx. All right, and so I'm going to use that substitution for all the sine functions in here, and I'm going to use that du over cosine of x to substitute for this dx right there. So that means our integral will become, okay, so this is just only some sort of like a marginal step right there, a step on that we put on the margin of the paper. And then the integral as a continuation becomes u to the 7 times 1 minus u squared and squared again. The cosine did not get a substitution, let's leave it there. But then that's multiplied with, now the dx is now substituted by du over cosine of x. And now we have our rights to cancel out the cosine of x. So our integral now becomes simply the integral of u to the 7th times 1 minus u squared, squared again, and du. It's a completely brand new integral, but very manageable. It's completely in terms of u, and it's just simply a matter of foiling out that 1 minus u squared, and we're going to end up with a polynomial. And of course, we're going to distribute that u to the 7th. So on my next board right there, okay, on my next board, then the integral becomes so u to the 7 multiplied with 1 minus 2u squared plus u to the 4th right here, du. And again, feel free to pause my video lesson here at any time to, double check for yourself how I got this. I just simply treated that 1 minus u squared as a 1 minus u squared times 1 minus u squared, and then foiled it out. That's all it takes. Okay, and then so now distributing out that u to the 7 to each term here, we're looking at an integral of u to the 7 minus 2 u to the 9th plus u to the 11th. Okay, and du. And so now in that way, now our final integral becomes 1/8 u to the 8th minus 2 over 10, okay, u to the 10th plus 1/12 over, times u to the 12 plus c. And then now we can go ahead and do some simplification on these coefficients and bring back the original meaning of the u variable. So u was substituted as sine of x from my other board. So here we're looking at 1/8 sine to the 8th of x minus 1/5 times sine to the 10th of x plus 1/12 times sine to the 12th of x. Okay, plus c. All right. So this is the final answer. Now, as long as getting a final answer here, it wasn't a challenging problem at all. It was not a challenging problem at all. But notice the way how the final answer here looked, and also combine this with the experience we have had back in example 3 earlier, before I brought up that generalization about this. But this answer here is, you see, we started out with an integral completely, it contains two kinds of function. There's a sine and there's a cosine of x right here. But now in our final answer, as an integral, as a final indefinite integral, everything here is completely in terms of sine of x only. Okay? Everything here is completely in terms of sine of x. And so, allow me to bring up a different solution. And then at the end, I'm going to generalize the whole problem for any one of my students or any one of the public viewers here to be aware of the kind of problem that might possibly exist out there, you might face out there when you're working with a trig integral where it's an odd power of sine coming together with another odd power but on the cosine right there. Okay, so here the major starting point was I tackled down on the odd power of the cosine. Okay, and now the same problem. And after we recognize that we have two odd powers, one on the sine and one on the cosine. So how about unlike the other route here, it's just a different route, same method actually, but different route. What if we tackle on that odd power of the sine of x right here? And so here's how it's going to look. If I treat that one as the odd power, if I decide to tackle down on that odd power sine to the 7 of x, then I'm going to isolate out, I'm going to separate out to become sine to the 6 times the cosine remains the same, power of the cosine remains the same, and that lone factor on the sine, I'm going to leave that at the end right here, sine of x dx. Okay, so very similar steps that was taken when we went the other route. And so now in that way, this sine to the 6 right here is understood as sine square to the 3rd power. So that means here we're looking at say sine square of x to the 3rd power, and then times cosine of x, cosine to the 5th of x times sine of x dx. So that's now in this route right here, in this route of the work, then cosine to the 5th stays the same throughout the whole problem. And so in that way, now in my next step, see, just like previous experience that we've already had, then sine square here is the same as, I'm going to rewrite that using the famous trig identity right here. I'm going to write that as 1 minus cosine square of x, okay, and to the 3rd power, and then there's a cosine to the 5th of x, okay, and then I'm going to times with sine of x with the dx additionally there. Okay, and so now in that way, okay, and so nothing unusual, it's just a different route. Instead of going with the tackling down on the cosine as earlier, now we tackle down on that sine to the 7 earlier. And so now at this point I am making my substitution alongside right here. I'm actually this time I'm deciding to substitute cosine of x for a new variable u right there. Okay, so cosine of x is to be substituted by a u variable. Then of course, just like usual, du dx is a negative sine of x. Okay, and that leads to saying that du over minus sine of x, or simply I can put the negative sign here, minus du times over sine of x is to equal dx. Okay, so the substitution is now ready for action right here. Okay, and a lot of I formed myself long ago. I formed for myself into a habit to always put the substitution process here in a box, kind of like in a sideway work right here, and then eventually we're gonna bring all that pieces back into our original problem. And so now in the actual current problem right here, then anywhere you see the cosine, we're gonna, of course, according to the substitution method, we're gonna substitute away the cosine. So now it's gonna produce for me 1 minus u squared to the 3rd power, okay, and then times u to the 5th power here, and then times with the sine of x, but did not, so this sign did not get a substitution because the substitution went for the cosine, and then multiply, but now dx here does get, and by the way, so they're all multiplication, right, as you already know. So dx here is substituted by a negative du over sine of x. Okay, and so in that way, now sine of x got canceled. Okay, and so our integral finally becomes completely in terms of u. It's a, okay, so how about, let's put it this way, minus u to the 5th, and this time I learned a little bit experience. Let's put that negative sign inside of the integral instead of putting it outside. Okay, so u to the 5th, and then 1 minus u squared cube du. So now it's another integral that's completely manageable. We can handle that in easily by simply foiling out that cubic right here and then multiply, distribute in that minus u to the fifth like that. Okay, so let's see how it happens. All right, so now on this, in the next step right here, minus u to the fifth stays the same, but I am now going to FOIL out the 1 minus the u square cube right there. So, in my experience, then it gives me 1 minus 3 u square plus a 3 u to the fourth minus u to the sixth, okay, du. So we ended up with a 4 terms thing, okay, and then I'm going to distribute out that u to the fifth, negative u to the fifth to each term like that. So consequently, I'm going to end up with minus u to the fifth plus 3u to the eighth, okay, minus 3u to the ninth, and then plus u to the 11th, okay, du. And so now that gives me, so now we are so ready for getting that final antiderivative. But for now, in terms of u first, so negative 1/6 u to the 6th power plus, right, and then 3 times a 1/9. So allow me to start doing some cancellation of the coefficient here. So it's now a 1. So it's supposedly 3/9, but now it's a 1/3 u to the 9th power minus 3/10 u to the 10th power, okay, and plus 1/12 u to the 12th power. And I wrote 15 for some reason. Okay, sorry about that. And we're adding c. And then we're going to bring back the original substitution of u. So that original substitution is still here. It's a cosine of x. Okay, and so now in that way, we are going to have a negative 1/6 times a, and I don't think I need parentheses here any longer. So cosine to the 6th of x plus a 1/3 cosine to the 9th of x minus 3/10 cosine to the 10th of x plus 1/12 times a cosine to the 12th of x plus c. All right, so there we go. Here's another solution of ours right here. All right, so we've come to another solution. So wait a minute. If we're now looking at the two routes right here, they came to quite different answers. The way how the answers come looks different. And again, I don't want to, I don't want to make the video too lengthy here. And so I'm skipping the part where we check, but we can always take the derivative on all of these terms together to make sure we land it back, on this original integral problem, right there, on this original function in the integral here. But so the point I would like to make now is that before in the earlier solution, now same problem, but in the earlier solution, all due to the fact that here we have two odd powers. It's a good thing. It gives us more options right here. So earlier I was tackling down on this odd power of the cosine to the 5th, and then we ended up with a. I mean, if you can always roll back on this video right here, rewind this video, and saw that earlier. But the answer in the earlier solution was completely in terms of sine. And the answer now, since now in this solution I tackle down the sine from the starting step, I tackle down the odd power of the sine right here, and then consequently it led to using cosine of x as a substitution. And so the final answer turned out completely in terms of cosine. So in that way, for this special little problem, be aware of the wording as following. That might happen to you. So now I'm introducing it so that none of you will get shocked when you see this kind of problem. It might exist. It will exist out there and might happen in your learning somewhere here and there. But the same problem, okay? And then, it's not the wording it's not simply just evaluate and here you go the integral, but instead it say evaluate with the given integral. But now sometimes the same problem, but asks you to evaluate the integral in terms of sine of x. So this problem here now with the extra wording on top. Now there are also problems just like that without this indication. Then it leaves you your own choice. You can tackle down on this odd power of the cosine or the other odd power on the sine. That problem without this instruction also exists out there. But now when in case you have the same problem, but you see both powers here on the sine and cosines are odd, okay, then you might see the kind of problem where evaluate and there's your integral, but in terms of sine of x. So in this way right here, it purposely route you into that direction where you have to, in this way, see, I want the final answer to be in terms of all the x term, all the sine of x term. So that means we have to tackle down on this cosine. We have to tackle down on the cosine and leave the sine, the odd power of sine the same, but splits the cosine here as cosine to the fourth and cosine of x, so that we can make substitution so that can become, you see, recall from that earlier work, sine to the 7 of x, and then here 1 minus cosine square of x. 1 minus sine square of x, and then times the cosine. Then in this way we are substituting u for sine of x, because we purposely want, see, in terms of sine of x. So we want to tackle down on whichever odd power so that it will allow us to substitute the sine of x away, so that finally when we return to the original variable, that it's all in terms of sine of x. Okay, and so just that same way, the same exact problem, there could also be the kind of problem where it asks you to evaluate, right, this integral over here, but in terms of cosine. Then now at this point in your experience, you know what to do. You're going to tackle down on the sine like that, so that eventually you can make this substitution for u equals cosine of x. Okay, and so this is just something to raise your awareness in terms that you're working with problems out there. And so now and it only happens when it's the special case where both powers of the sine and cosine are odd. Then you have that special kind of problem where it does narrow your attention a little bit to, hey, it only wants you to proceed with this problem, but produce a final answer completely in terms of cosine or completely in terms of sine. Okay. All right, so now let's look at the last example in my particular lecture here, and in this example I should be able to point out the last case of those integrals, those trig integrals in this family of a power of the sine on a power in product with a power of a cosine. Okay, so here in this problem allow me to introduce the last case. So we have seen the different cases throughout example 3 up to now. So now in example 5, again, it's another problem where we want to evaluate. Okay, and let's look at the following integral. So the integral we want to find here is, how about sine to the fourth of x times cosine square of x. All right, and so just like I said right before we begin with this example over here, then this family here, this trig integral problem is apparently one member in the family of those integrals where it comes from a power of the sine in product with a power of the cosine. Okay, but now further as an observation, and this is what makes the problem itself stands on its own as one example, because it brings in its own tips and tricks to get through the problem right here. It has its own style to approach the problem. So here, even though there are both a power of either sine or cosine, but now both of these powers are both even. Okay, so these two powers are both even, and that's one thing we want to notice about. And so Admittedly, it will make the problem longer and slightly more challenging, but it's still within our manageable ability. Okay, it's still something that's manageable within our capability, and so now allow me to get in how we start with that. So keep in mind again, these two powers, the power on the sine and the power on the cosine, they're both even. So now, because they're both even, so whichever the approach I'm about to introduce here, it will apply. It can be applied to either one of them. So how about for now I'm going to tackle on the power of the cosine. Okay, the power of the cosine, and so the reason for now I tackle on the power of cosine is simply because out of observation I noticed that the power on the cosine, at least between the two even powers here, then the power of the cosine is a little lower than the power on the sine. And so and we will see better usefulness of choosing the lower power, even though it will also work if we choose the power of sine. But so let's look into the general idea of the problem first. So they're both even, and so I picked cosine square. So simply just as what I picked, as a problem that I picked, then how about sine to the fourth? I'm leaving it the same, but the cosine square, since I chose it, I chose that one. So I'm gonna, and the purpose that choosing it so that I can rewrite the square here as a 1 minus sine square of x. And with the dx. Okay, so the advantage of any even power is that we can recall that if we're looking at cosine of an even power 2k, then in the earlier examples I brought up a generalization that we can always write that as a cosine square and then raised to the k power. So this is obviously cosine square and raised to the first power. And so now that standard trick that we've been doing a lot in earlier examples, we rewrite the square here individually as a 1 minus sine square of x right here and raise that to the k. That's some generalization that can be seen, that can be used again, reapplied here from earlier examples. And so that's what I was doing here. So now that means we are, in the next step, we're just simply going to distribute that sine to the fourth to each term here and produce for ourselves an integral, the next integral of two terms. So one of them is a sine to the fourth of x, and the other one is sine to the sixth of x and dx. All right, and so in that way we are forced to break it down into two separate integrals. One of them is a single power sine to the fourth of x, and the other one is another integral, single power sine to the sixth of x dx. Okay, and so now before I get any further, so that's just a general starting point right here. And then what's the plan for next? The plan for next here is, see, observation now telling us that any of these is simply a single power, so we can use the reduction formula effectively here. And again, they are needless to say, they are definitely even powers again. So any of these is even power. So when we recall from example 1 that I brought up earlier, then so when the power and when the single power on any of these is even, then pretty much the best choice of work here is to use the reduction formula. The worst thing that will make the problem a little challenging is that we have to apply the reduction formulas on the two separate integrals here, because in the end we have two separate terms. So we have to apply the reduction formula on the two separate the terms right here. But then hold on to what I said. Actually hold on to what I said, because experience. I want to pass on a little bit of experience down to, so yes, the plan technically is that we have to apply the reduction formula on that and the reduction formula on this. But there is way that we can work things a little more effectively instead of just cranking through the reduction formulas. Okay, so the wait and see for that. But then definitely the plan, as a bottom line, the plan is we definitely going to have to use the reduction formula, and here it's a power of sine, so we're going to use the reduction formula on the sine for the sine function on the power of sine. Okay, and then when it comes to these kind of problems, and I should have also mentioned this in earlier examples, when it comes to trig integrals problems, please forgive me if I make any simple arithmetic errors throughout my lecture, and even if I make errors, it only impacts the value of the coefficient in front of each of your term, but in the end it should not, no matter how badly I make the errors with these arithmetic errors, it should not impact the overall structure of the problem. So as you follow along with the videos here and you recognize any error that I made in terms of adding and subtracting fractions and all that, please forgive me on that, okay? But again, it will not impact the general structure of how we tackle down these problems. The reason I have to say that now is that it's going to get pretty lengthy, and it's the way, it's the nature of these problems right there. And so I am just a human being like anybody else, so I make mistakes, and you know, if I recognize my mistake right on scene right here, allow me to maybe roll back and erase a couple lines and fix the errors. But otherwise, as I said, it will not impact the main structure, the main idea, and the main structure of the problem at all. Okay, so in that way, now allow me to get started. So in this way right here, at this current step, yes, I will be using the reduction formula for the power of sine. But here's the thing, we're gonna work a little bit with a little bit of a clever plan right here. I am not going to apply the reduction here and the reduction here, the reduction formula for that and the reduction formula for that. Because, you know, naturally speaking, when you see two terms, you're gonna start thinking, oh my god, we're gonna have to apply the reduction formula on both of these, so two separate works, and then each one of these lead you into the next step of reapplying the reduction formula. So it seems a little scary at first, but it's actually not that bad. So my advice here is, once you've had all of your terms successfully written down in terms of, and you can see that this is it has a certain order of the power, so there has to always be some term with the highest power on the sine, some term has the highest power on the sine. In some other problem where things can get a little lengthier, then we might end up with 3 or 4 terms, but in the end they're all in terms of one function, sine of x or cosine of x, but one function. But then among all the terms, there will be one highest power. So throughout my two terms here, the highest power I recognize is a 6. So I will only apply the reduction formula on that highest power. Only apply the reduction formula on the highest power. That's the effectiveness of working with the reduction formula. You definitely don't want to have two separate works. You're gonna need two separate pieces of paper. Stay away from that. Okay? And so, quick reminder. The reduction formula says when you are handling sine to the n of x as one single function, then the reduction formula says we need to produce the following. So the formula says you're gonna end up with negative 1 over n times sine to the n minus 1 of x times cosine of x. But that's not all. We're gonna need to add with n minus 1 over n times an integral of another power of sine, but lower, so n minus 2 of x. So sine to the n minus 2 of x dx. That's a brief reminder about the reduction formula for sine to the n of x right there. All right, and so in that way, so now back on my first board, I am going to apply that reduction formula for sine right on that term. So I am going to purposely leave this hanging there. So that integral of sine to the 4th of x for now remains the same. Okay, and you will understand that later. Minus, so now so be careful with the sign right here. It's minus. So now I am going to produce for safety of the work, I am going to produce a pair of parentheses to contain whatever comes out due to the reduction formula on this separate integrals. And even that minus sign is kept in front, outside of the parentheses, so that I can have a clear sense about how I apply directly that power of that reduction formula on the power of sine here, the power 6. So that means in this case I'm looking at, according to the formula, now I'm looking at a negative 1/6. I'm just follow one by one, right, with the reduction formula, times sine to the 5th power, because the power here got reduced by 1 in that non-integral term, and then multiply with the cosine of x. And then I need to add, now with that power n being 6 right here, because specifically right now we're applying the reduction formula for this high power where the power n is 6. So that's why it's 1 over minus 1 over n, and then here it's going to be n minus 1, which is 5, and divided by n, which is 6. So 5/6 times with an in product with an extra integral here being now sine to the 4th of x dx, and that completes what's inside of my pair of parentheses here. Okay, and so now in the next step, see, notice the first term still stays the same, the integral of sine to the 4th of x dx. But now I'm going to start distributing. I'm going to start distributing that negative sign into each term so that I can remove the parentheses, and then we're going to start recognizing like terms and all that, and it's going to start being surprised. It's going to start surprising us from that point. So now the minus in front of the parentheses, but distributed to the first term inside parentheses, it becomes plus 1/6, okay, sine to the 5th of x times cosine of x, okay, plus, and actually here it's a minus because the negative sign distributed in, minus 5/6 times the integral of sine to the 4th times dx. All right, so ladies and gentlemen, the reason I said earlier that you didn't need to, and you will never need to handle two separate works for two reduction formula, because here you started out with the highest. You started out applying the reduction formula on the highest power from the earlier step. On the highest power, I apply, so throughout the two terms we have here, I apply only the reduction formula for the highest power on that integral containing the highest power of the single sine of x right here. And then as we break it down, and it will reduce to another step, and eventually it's going to land into a step where we can combine like terms. So now I'm using that word. We can algebraically combine like terms. These are like terms. And so it starts making things more efficient here. Okay, so combining these as a like terms, and now I have my right to put this as a front term, because this one here is done from being integrated from the integral problem. So now I'm going to leave the positive 1/6 times sine to the 5th of x times cosine of x. Okay, and then this is coefficient 1 multiplied with that integral. So coefficient 1 minus with 5/5 is going to give me a positive 1/6. Okay, multiplied with the integral sine to the 4th of x dx. And now we realize that we have a much simpler problem already. Okay, but now this integral still needs further attention, because we didn't get there yet. We still have to find out what that integral will turn out. But at least we already had some terms done. Okay, and so now I am going to leave the first term, and this term will remain the same for the rest of the steps. So this 1/6 times sine to the 5th of x times cosine of x, plus, now I'm going to put the 1/6 as a coefficient, and I'm going to now produce a pair of parentheses. Okay, and ready for applying directly that reduction formula on this high power of this single high power of sine of x right here, sine to the 4th of x, and it's an even power again. Okay, and so now the formula says I need a negative 1/4, because the power n currently now in this current step that we applying the reduction formula, it's a negative 1/4 times sine to the 3rd power. We reduce that power by 1 times cosine of x. Okay, and then I'm going to have to produce as a term that's added to this. Now the power here currently is 4. That's n equals 4. So n minus 1 is 3 divided by n. So 3/4 times an extra integral that we have to produce here according to the formula. but now it's sine squared of x dx. All right, and so that's how it works. And so now at least, see, the power already, so we still runs into another integral, but the power, the single individual power on that sign has already reduced to a much lower power right there. And so guess what? We can apply that again, but before we can do that, let's go ahead and distribute this 1/6 to each term. Okay, so now I'm looking at, this 1/6 sine to the fifth or whatsoever here is staying the same. Okay, sine to the fifth of x, cosine of x. Okay, but now 1/6 multiplied with negative 1/4 give me a minus 1 over 24 sine cube of x. Okay, cosine cube of x, right, plus, and then now multiplying this 1/6 to that 3/4 right there, it's going to give me a, so 1/6 more, and the 6 cancel with the 3 a little bit, so it's give me a 1/8. Okay, so this is going to be a 1/8 times the integral of a sine of the sine squared of x dx. All right, so we're at some much easier steps now. Okay, so now with all that, so now these two for the rest of the steps, the plan now is I am going to apply the reduction formula on this again. Okay, but then other than that, all of these terms that already got out of the integral sign, these will stay the same or remain the same for the rest of the steps here. So the first term here is a positive 1/6. Okay, sine to the fifth, okay, of x, cosine of x, minus 1 over 24 sine cube of x, cosine of x, and plus, so now I keep 1/8 as a coefficient. And now I'm going to open a pair of parentheses. This, again, ready to use the reduction formula for this. So the power now is reduced to, at this current step where we're about to apply the reduction formula, then n equals 2 at this point. And so now it's going to be a negative 1/2 times sine of x times cosine of x. And then I'm going to need to add, so now 1 minus n minus 1. So in this case, it's going to be a 1 over n, which is 1/2, times an extra integral. Now sine square, but minus 2, so it's going to be just sine to the 0, which is 1. And so now we have the final integral here, just a simple integral of the dx, which is really, it's a 1 times dx. And you have seen how the application of the reduction formula has worked earlier. So I don't think I ever need to write that times 1 anymore. And you have seen my clarification about this kind of symbol as well. Okay, and so now at this point we are so ready for getting that final integral. Okay, and so allow me to go back to the other board right there. Okay, and so now I'm going to erase this step right here. All right, actually these two steps. All right, and then so now my final answer here is going to be, so carrying over from the other board, so now it's 1/6 sine to the fifth of x, and then cosine of x minus 1 over 24 sine cube of x times cosine of x, okay, plus, and now I'm distributing out that these terms here to get ready for the final work. So it's now going to be a minus 1/16 sine of x, cosine of x, okay, and then plus 1/16 times the integral dx. Okay, and so now the last and the very, very final answer is going to be a 1/6 sine to the fifth of x, cosine of x, all right, and minus 1 over 24 sine cube of x, cosine of x, okay, minus 1/16 sine of x times cosine of x, and plus, and now that simply gives me an x over 16, okay, plus c. And that's how we complete. So this one right here is the box that put our final answer, okay, in the box like that. All right, so okay, so I apologize about forgetting to turn over to the board, but so that term remains the same here, and then this term remains the same, and so from that very last step to this step right here, the only thing is now taking that final integral right here that gives us this value, okay. All right, so with this work here that I'm doing, now back in the beginning, so we got the idea about we got two even powers, and so I just simply picked one and then re-express that as using that either cosine square equal 1 or 1 minus sine square, or if I picked on the signs right here on that even sign, then I'm gonna have to utilize that identity sine square equals 1 minus cosine square right there. But then in the end, the point now is that from an integral like this, we can re-express them into an integral completely in terms of, so if I pick the cosine in the beginning, then my very last integral right before we start getting into it, right before we start applying the reduction formula, is completely in terms of sine, and it's a combination of all the even powers of the sine right there. So we got multiple terms. We ended up with a multiple terms with different even powers of the sine. Okay, and so that's the route that I did here in this problem. Now it's going to be lengthy, but allow me to erase the work here on the same exact problem, and I can just point out a different direction. We don't have to, in this next step I'm about to do here, we don't have to follow the whole problem, but I can point out. So as I said earlier, the two powers here are both even, and I purposely tackle down on the cosine square right here. So we had a choice from the beginning as well. We had a choice to tackle down on that sine to the fourth like that as well. And so if we tackle down on the sine to the fourth, now I am going to write the sine to the fourth here as sine square of x square times the cosine squared of x dx. So now I'm talking about tackling down that other power. They're both even, so now I'm tackling down on the other power, the higher power. So at my first try, I tackle down on the lower power. But now look at what it happens to us here. If we're going this way, then now the sine square of x is rewritten as 1 minus cosine squared of x, and all square, and we're multiplying that with the extra cosine squared of x that remained from the previous starting problem, the starting of the problem. And so now you can start having a sense that this is completely in terms of cosine. So opposite from the other one. And furthermore, we can now start foiling out this square over here. It's a square on the difference. And so that means in the extra step here, I'm going to have to FOIL out, and I'm going to end up with so 1 minus 2 cosine squared of x plus a cosine to the fourth of x. Okay, and then I'm going to have to multiply with that lone cosine squared of x. Okay, and then we can distribute, or I should have said distribute the cosine square for each term here. Okay, and so doing that, then my next step, which brings me into a final integral setup before we start applying the reduction formulas and all that. The final integral is as following. So the cosine squared multiplied with 1 runs into a cosine squared of x minus, so now 2 cosine squared times the cosine square is a 2 cosine to the fourth of x plus, okay, and now I'm looking at cosine to the sixth of x dx. So now from here we're going to start being able to apply, we're going to start applying our reduction formula, but this time, since our integral is an integral of 3 terms containing all in terms of the cosine, so I am going to have to use, for this one here, we're going to use the reduction formula for cosine. So as a reminder again, So as a reminder, then the reduction formula for cosine to the nth power of x says we need 1 over n times cosine to the n minus 1 of x times sine of x. Okay? And then we're going to add n minus 1 over n times cosine to the power n minus 2 of x dx. And that's the reminder about the reduction formula. And so, and then again, once we have reached to this point to a final integral before we start handling it, then our integral as a checkpoint, our integral, just like the earlier step I've done, our integral should be an integral completely in terms of 1. What do I mean by 1? Either sine or cosine, but only in terms of one expression among the two here. So here we are completely in terms of cosine. And it's a combination of all these different powers. Yes, there may be some coefficients. It depends on, it came out from how we FOILed out this. Okay? And so, and then the plan, just like how I worked with this, with the earlier problem, with the earlier solution, same problem with the earlier solution when I tackled down this. Then when we came to this final integral before the real action right there, then for the next step I would choose to effectively work, and because here we got 3 terms. We actually realized a little disadvantage of going this way, and that's actually the reason why I chose to go the other way, tackling down on the lower even power right there, simply because the early solution ended up with less terms in this final integral compared to the one we have now. The one we have now has up to 3 terms here. But in the end, it doesn't matter. Really avoid to produce for yourself 3 separate the integral. I mean, the reduction formula is work right here. That's way too much. Start out with the highest power. Apply the reduction formula on this highest power first. And then just like how you saw that earlier in the earlier solution, then we can some integral is going to be combined as like term with this x to the 4th, and then still holding on to that one, use the reduction formula on that cosine to the 4th. Okay, and then it's going to become something to the square power. Then we're going to combine power with that, combine as like term with that, and then eventually the finish our problem like that. Okay, but so. Yes, as I kind of said that earlier, the reason I didn't choose to go this way, and of course allow me to stop this plan here, like that. But the reason I chose to tackle down on the lower even power here, simply as my own personal experience, I found that, and you saw that through the board right here, when we worked it out and we ended up with an integral, a final integral that's less terms compared to this. Okay. So, and that's the reason why. So less term is always somehow easier and to manage, right? Somehow, you know, a lot more manageable compared with something so lengthy like this. All right, but again, do accept the fact that there will be times where these kind of problems become very lengthy, and you just have to be responsible to keep track of all the errors. And I already said earlier, I can never guarantee that even throughout my work that I've done earlier, I can never guarantee that there was error-free. Okay, I can never guarantee there was no error. So forgive any of my arithmetic error on the coefficients if I add and subtract terms a little bit incorrectly, but that should have not changed the way how the structure of the problem is. Okay.